All right, a piecewise function is a function that has to be defined in pieces because it is not just a graph that can be written as one equation. We have to define it over different intervals of the x-axis. So this function says f of x equals negative x minus 1 for x less than negative 1. It equals negative 3 for x between negative 1 and 2. And it equals the square root of x minus 2 for x greater than or equal to 2. And so we want to find the value of the function on for different values of x. So when we have f of negative 3, we are looking at this part of the graph when x is less than negative 1 because x is negative 3. And during that interval, anytime x is less than negative 1, the function acts like the line f of x equals negative x minus 1. And so the value of that function at negative 3, we would plug it into that equation. So it would be negative 3 minus 1, which is 3 minus 1, which is 2. And you can see that on the graph. When x is negative 3, the function has a value of 2. F of negative 1 happens when x is between negative 1 and 2. And so that always has the value f of x equals negative 3. It's always negative 3 in that interval. And so there it is right there, negative 1, negative 3. And then when f is equal to 2, we're talking about this part of the function, when x is greater than or equal to 2. And when that happens, the function has the value square root of x minus 2. So that equals the square root of 2 minus 2, which is the square root of 0, which is 0. And you can see the point right there. F of 6, that also happens in that area when x is greater than or equal to 2. And so we would put it into that same thing. Square root of x minus 2. Square root of 6 minus 2 is the square root of 4, which is 2. And you can see that on the graph right over here. You can't really see it. It's off the edge. But when x is 6, y is 2. And so that's what that point is. The value of the function at 6. All right, so let's look at these two. Graph the function defined by f of x equals negative 3x for x less than 1 and f of x equals negative 3 for x greater than or equal to 1. All right, so we're looking at two different areas of the graph of the coordinate plane when x is less than 1, so over here on the x-axis, and when x is greater than or equal to 1, so over here. And we're going to see what the graph is doing. So we're going to look at the green part first. We're going to look at the area where x is greater than or equal to 1. All right, so what's happening there? When x is greater than or equal to 1, the function has a value of negative 3. That's it. It's always negative 3. So when x is 1, it's negative 3. When x is 2, it's negative 3. When x is 3, it's negative 3. And forever and ever, as x goes up, it's always negative 3 in that part of the function. So it's just the horizontal line, y equals negative 3, and that's what the function looks like from x greater than or equal to 1. Now let's look at the yellow part. When x is less than 1, what does the function look like? The function, when x is less than 1, looks like f of x equals negative 3x, which is the line with y-intercept 0 and slope negative 3. 0, 0 is on that line, and then we know the slope of the line is negative 3, so we can go up 3 and back 1 and find another point. And so this part of the function, when x is less than 1, looks like this line. All right, for the one in example 6, f of x is equal to x plus 3 when x is less than negative 1. So in that part of the function, we're talking about the places where x is less than negative 1, so this area. And then for the second part of the function, x squared for x between negative 1 and 2. So this part of the function is right here. So let's look at what's happening. In the green part of the function, when x is less than negative 1, we do want to put an open circle when x equals negative 1 for that particular function. So when x equals negative 1, that function, x plus 3, would have a value of 2. And so we're putting an open circle there just to show that we want all the points to the left of that, but we don't want to include that value of x. So we know that this is going to be a line, x plus 3, f of x equals x plus 3, with y-intercept 3 and slope 1. And we get this line, y equals x plus 3, for the values of x less than negative 1. And then as x goes from negative 1 up to 2, not including 2, we have the function f of x equals x squared, which is a parabola. And so at x equals -1, we're going to have -1 squared, which is 1. So the point -1, 1 is on this parabola. And then the point 0, 0 is on the parabola, and 1, 1. And so not including x equals 2, which would have a value of 4. And so we're putting an open circle there. So from x equals -1 to 2, we have this parabola for this function. Okay, so we're looking at the greatest integer function. So graph the greatest integer function, f of x equals greatest integer less than or equal to x. So if x is -1.7, we'll just go ahead and graph some points. So when x is -1.7, we are looking for the integer, greatest integer less than or equal to -1.7. And that's going to be -2. And so -1.7, -2 is on this graph. The greatest integer less than or equal to -1 is just -1. So the greatest integer function of an integer is that integer itself. So -1 is going to be on this graph. Now, -0.6. The greatest integer less than or equal to -0.6 is -1. So you're looking for the integer that is just less than whatever that number is. So it's the integer you would find if you go to the left on the number line, the first integer you come to, that's the greatest integer less than or equal to whatever your number is. Unless it's an integer, and then you just stay there. So for -0.6, the next integer down from that is -1. So the point -0.6, -1 is on this graph. If x is 0, the greatest integer less than or equal to 0 is itself 0. At 0.4, we're just above 0, and so the greatest integer less than or equal to 0.4 is 0. So the point 0.40 is on this graph. If x is 1, the greatest integer less than or equal to 1 is just 1. So the point 11 is on this graph. At 1.8, we're talking about the integer that is just less than 1.8. It's less than the next integer down, so 1. I'm just stressing this because sometimes it's hard to understand when I just say it really fast. So 1.8, the greatest integer less than or equal to 1.8 is 1. So the point 1.81 is on this graph. When x is 2, the greatest integer less than or equal to 2 is itself 2. For 2.5, the greatest integer less than or equal to 2.5 is still 2. So the point 2.52 is on this graph. Okay, so you can kind of see what's happening here. This looks like little stair steps, because whenever you hit an integer, you stay on that integer until you get to the next integer for your y value. So if you look at, say, when x is -1. When x is -1, y is -1. And for all these x values in here, it just keeps staying -1, -1, -1. It doesn't change, because for all those x values there, the integer that is less than or equal to them is -1. So the function stays at -1 until you get to 0 on the x-axis, and then the greatest integer value of 0 is 0. So once you get to 0, that stair step stops, and you hop up to the next stair step where all the x values here just always have the value 0 for their y value, because the greatest integer less than or equal to 0.1, 0.2, 0.3, all those have a greatest integer value of just 0, because it's the next integer down from whatever that thing is. So you keep staying at the same y value until you get to x equals 1, and then the y value jumps up to 1, because the greatest integer less than or equal to 1 is 1. So you have an open circle here, and you hop up here, and now for all the x values between 1 and 2, you stay on the integer 1 until you get to x equals 2, where you're going to pop up to here. So there'll be an open circle here, and you'll pop up to the next step and so on. So this is what the greatest integer function looks like. It looks like these stair steps where you stay on the same integer for your y value until you get to the next integer up. Okay, now we're going to look at a piecewise function that goes with a certain real life situation. All right, a salesperson makes a monthly salary of $3,000, plus they get a 5% commission on sales over $20,000 for the month. So we're going to write a piecewise function to represent the person's monthly income, I of X, in dollars, for X dollars in sales. There's two situations. If they only accomplish 20,000 or less in sales in a month, then they don't get the bonus. They get $3,000. That's their salary, I of X. If they sell over 20,000 in a month, they're going to get 5% commission, which means 5% of the total value of the sales they get over $20,000. So if they sell $30,000 worth of stuff, they're going to get 5% of that extra $10,000 back in their paycheck. So they're going to get the $3,000 they always get plus 5% of that money, that amount of merchandise they sold over $20,000. All right. So X is the amount they sell. X minus 20,000 is going to be the amount in sales over 20,000. Okay. So what's going to happen? If you make over 20,000 in sales, you're going to get paid 3,000 plus the extra 5% of whatever you sold over 20,000. So the piecewise function is going to look like this. I of X, so your income on X is the amount you sold, the amount of products, the value of the products you sold that month. If, there's two situations, if the amount of stuff you sold is less than or equal to $20,000, meaning you didn't sell over $20,000 worth of merchandise, then you're going to get $3,000. Your income will have a value, your I of X is 3,000 if X is less than or equal to 20,000 in sales. However, if you sell over $20,000 worth of merchandise, if X is more than 20,000, then you're going to get your $3,000 plus 5% of the amount you sold over 20,000. So that's going to be X minus 20,000. So this is your piecewise function. Two situations. You sold less than or equal to $20,000 in merchandise, in which case the function is 3,000. Your income is 3,000. If you sold more than $20,000 worth of merchandise, you still get your 3,000 plus 5% of the value of the merchandise you sold over $20,000 worth. Okay, so we're looking at intervals of increasing, decreasing, and constant behavior in a function. Suppose that I is an interval contained within the domain of a function f. F is increasing on I if f of x sub 1 is less than f of x sub 2 for all x sub 1 less than x sub 2 on I. F is decreasing on I if f of x sub 1 is greater than f of x sub 2 for all x sub 1 less than x sub 2 on I. F is constant on I if f of x sub 1 equals f of x sub 2 for all x sub 1 and x sub 2 on I. That is very complicated sounding, but it really is easy to understand if you just look at a picture. F is increasing. Okay, so this function is increasing. One on the far left is increasing. The reason it's increasing is because as x gets bigger, y gets bigger. So as you go from x sub 1 to x sub 2 in this interval, just this little interval here, and we can talk about any interval on the graph of a function and talk about what the function is doing. All right, so this particular function here is increasing as you go from x1 to x2, meaning that for any x sub 1 that is less than x sub 2, f of x sub 1 is going to be less than f of x sub 2. So as x increases, y increases. That means it's an increasing function on that interval. So That's all that this first sentence here means. Then decreasing. A decreasing function, if it's decreasing on a certain interval from x sub 1 to x sub 2, that means as x is going up, y is going down. Okay? So that means x sub 1 less than x sub 2 means f of x sub 1 is greater than f of x sub 2. So as x goes up, y goes down in that interval between x sub 1 and x sub 2. That's a decreasing function. Constant means that as you go from x sub 1 to x sub 2 inside a certain interval, the function doesn't change. It stays the same. Okay, so that is all that these three statements mean. In the first instance, that's an increasing function, decreasing function, constant function on those intervals. Now, functions do all kinds of different things. Some go up and down and all around. So you have to choose an interval to talk about what the function is doing, because you can't always say it's doing this all the time. You can say it's doing this between x sub 1 and x sub 2. This is what it's doing. So we want to talk about functions and their behavior. Okay, so let's just use interval notation to write the intervals over which this function is increasing, decreasing, and constant. All right, so if you look at the graph, what is it doing? As you start on the left, going left to right on the x-axis, as you start at -4 for x, the function is now decreasing. It's going down. As x is going up, y is going down. Then once you get to -1 on the x-axis, so here, the function starts to be constant, stays the same until you get to 2 on the x-axis, and from 2 to 3, the function is increasing. And once you get to 3, the function starts decreasing again. Okay, so we're going to write intervals for when the function is doing different things. Let's start with constant. It's constant from -1 to 2. So we'll put the interval notation here for constant, -1 to 2. From -1 to 2 on the x-axis. This is not a coordinate pair. This is not the point -1, 2. This is an interval. So remember, to know what it means, you've got to know the context. In this context, we're not talking about a specific point. We're talking about an interval on the x-axis. As you go from -1 to +2, the function is constant. Okay, when is the function increasing? I'm going to go to increasing now. The only time the function is increasing is between 2 and 3 on the x-axis. So the interval where the function is increasing is the interval 2 to 3. And the reason I'm only using parentheses and no square brackets is because you can't really talk about what a function is doing at a specific point. So you would never just put, a solid bracket when you're talking about increasing, decreasing, or constant, because a function is not doing anything when it's at a specific point. It's doing things across an interval. It's moving. If you just, say, what is it doing at the point, 3, when x is 3? It's not doing anything. It's just one point. So you always use parentheses when you're talking about intervals where a function is doing things. Decreasing. Okay, the function is decreasing in 2 places. It's decreasing as you go from -4 to -1 on the x-axis, and as you go from 3 to infinity on the x-axis. The function is decreasing in both places. So for the decreasing, we're going to say the interval from -4 to -1, sorry, union the interval from 3 to infinity on the x-axis. So those are 2 places where the function is decreasing. As x increases, y decreases. Same thing for 3 to infinity. As x is getting bigger and bigger, y is getting smaller and smaller. Negatively, it's going down. All right, so relative maxima and minima. All right, a relative maximum for a function is just a place where f of a is greater than or equal to f of x for all x near a. So what all this means is that if you're talking about a little interval around a certain x value, a relative maximum is where the function has the highest value in that particular area. So sometimes when we're dealing with a function, we want to talk about places where the function changes behavior. And those will be relative maximums and relative minimums, because as you're on this particular function, you're increasing. And when you hit this spot, the function changes behavior. It starts to decrease. And so those places are called relative maximums if it's the highest spot or has the greatest value of f of a in, an area close to x equals a. Or a relative minimum value like this, f of b, when you're close to x equals b. All right, so when you're close to b on the x-axis, this value of the function is the lowest value. So f of b is less than or equal to f of x, the other points, the other function values near b, when x is near b. So informally, the definition of a relative maximum and minimum is that f of a is a relative maximum of f. It means that f of a is the maximum value of the function relative to other points nearby. And f of a is a relative minimum of f if f of a is the minimum value of the function compared to other points that are close by. All right, so this is talking about behavior really where the function begins to change behavior. But we want to often know if that's a relative maximum or relative minimum, and we want to know the exact place where the function is changing behavior. So this is not really, we're not going into all that detail now. Right now, we're just talking about what is a relative maximum, what is a relative minimum. And it's just a place where the function reaches the highest value in the direct vicinity of that point. All right, so for the graph of y equals g of x, determine the location and value of any relative maxima and minima. All right, so you can see what's happening. The function, let's start on the left, always starting on the left, the function is decreasing, going down, until you get to this spot right here, and then it starts increasing again. And so a place where the function is decreasing and then it starts increasing is going to be a relative minimum. So it comes down, and as soon as it gets ready to go back up again, that's where you're going to have a relative minimum. So this function has a relative minimum at x equals -1. -1, -5 is a relative minimum for this function. And then it's increasing, and once it hits x equals 2, it begins to decrease again. So if a function is increasing and then it switches over to decreasing, we know that we just hit a relative maximum. Okay, and that's at the point 2, 1. We have that relative maximum. So then the function is decreasing until you hit x equals 4, and then it starts increasing again. So that's another relative minimum. It's a low spot in the function. And that is at 4, -2. So when x equals 4, you have a relative minimum. When x equals 2, you have a relative maximum. When x equals -1, you have a relative minimum at the point -1, -5.